Hello and good morning, CTS265 Section 840 students for the Fall 2016 semester at Anne Arundel Community College. This morning's video tutorial is going to be on the Cisco Networking Academy Lab 2-1, where we're going to be taking a look at EIGRP load balancing. In fact, I believe we're going to be doing some equal cost load balancing as well as unequal cost load balancing. As all of the NetAcad labs, or as I do for all the NetAcad labs, all of the IP addressing that you see is already in place. That way we don't have to spend a bunch of cycles typing in IP addresses. Please take note that according to the lab, they're saying this is router 1, router 2, and router 3. So I've got that information here. These are all physical Cisco either 1841s or actually 9 and 8. These are 2811s. But they're running 15 code, right? All of the routers are running 15 code. And my router numbers are going to be 6, 9, and 8. But you can see 6 corresponds to 1, 9 corresponds to 2, and 8 corresponds to 3. So let's go ahead and dive in onto the command line here and get things started. So on step 2, one of the first things we're going to do is we're going to enable, we'll go from user exec to privilege exec, and then into global config, and we're going to say router EIGRP 100. Now we're using classic mode here because again we're going to be talking about load balancing. We're going to be looking at the feasible distance, the computed distance, the reported distance, and things like that. And so in 64-bit mode, it's just not conducive to dealing with the metrics, because 64-bit metrics, as you saw, when they start to scale or they go on that 64-bit scale, the numbers become just overwhelming in some cases. So we'll say router EIGRP 100, and then we're simply going to say network 10.0.0.0. We're just going to kick it on for all of the 10 networks. Now again, I don't need a wildcard mask here, because if I exclude the wildcard mask, EIGRP looks at what I just entered and says, oh, well, you must want this to be at the classful network boundary. So a /8, and it's going to do that for us auto-magically. So if I were to say do show IP EIGRP interfaces, you can see, take a look at that, boom, right? We throw that single network statement in there, anything in the 10.0.0/8 space has the EIGRP process running on it. Now, it doesn't have us do this, but this might not be such a bad idea. We're not going to be establishing adjacencies over those loopback interfaces. So I'm going to say passive interface default, and then we're going to say no passive interface serial 000 and 010. Again, on the interfaces on which I need EIGRP running, I say no passive interface. Again, those loopback interfaces, we're simply not sending hellos, but they are still going to be advertised into EIGRP. So if we take a look at our final section here, it's do show run section EIGRP. Excuse me. You can see this is what we have. So what I could do is I could simply grab this, right? Because we're using the same configuration that's going to be placed onto router 2, which is our router 9. So if I come over here to router 9, and we'll go from user exec to privilege exec into global config, I could simply paste that in there, right? And as you can see, the neighbor relationship between router 2 and router 1 has now been established. So we have an adjacency between router 1 and router 2. So if I say do show IP, do show IP EIGRP neighbors, you can see there is the handle, the H column, right? The handle column. Starting at 0, that's the first neighbor that was learned. Out the interface serial 000. We've got our hold time, right? Every 5 seconds we should see that update. The uptime, how long the adjacency's been there. Smooth round trip time and the RTO, the retransmission timeout value. And the sequence number. In terms of the reliable packets, the last sequence number I saw in the reliable packets being sent back and forth. So now what we're going to do is we're not only going to debug the IP routing process, but we're going to debug the IP EIGRP for this autonomous system, the specific autonomous system number, on router, or what would be considered router 3. It's going to be our router 8. So we'll get into global config here, and I'm going to say do debug IP EIGRP AS, or actually no, I have to put the AS 100, and then debug IP routing. Right? So we've kicked off a bunch of debugs here. Now remember, I'm actually doing the exact same thing on this router in terms of from a configuration perspective as I am on the other router. So I could simply I had highlighted 4. So I can't paste it in right yet, but let's come back over here and we can just simply copy and paste this information, right? And this gives us a pretty solid EIGRP configuration. We've got the correct passive interfaces. And there are the debugs, right? The IP routing debugs as well as the EIGRP debugs. And let's scroll back up a bit here and talk about some of the output we're seeing. So you can see we've got the syslog messages coming in, telling us we've got the adjacency. It passives the interface, but the adjacencies do establish. And then we get the routing table updates, right? So updating EIGRP 10.1.102/29 via 10.1.103.1, the serial in the serial interface here. So we're adding this routing information into the routing table. You can see we've got the metric information on the side here, our computed distance to the right, and the administrative distance to the left. Remember that the administrative distance for EIGRP is 90. So we have all of our metric information being entered in here. We can see that the neighbor 2 to 3 relationship comes up, and then we have other information getting added in. All right, so now if I was to say do show IP EIGRP neighbors, I should see 2 neighbors, and I do. Both router 1 and router 2 do show IP EIGRP topo. So let's take a look at the topology table. So remember, the bandwidth has been set to 64 on all of our links. And so when we take a look at what we've got here, again, everybody's in the passive state, or everybody that we can see here anyway is in the passive state. So when we're looking at the information here, you can see that this is our successor route. And we have 2 successors. And those successors have identical computed distances, which at this point in time, at this very moment, happen to be the same as the feasible distance. But remember, this is our computed distance. And this distance here, this metric here, can change dynamically and could be different than the feasible distance. And then we have the reported distance. And let me throw 40,512,000, right? And then this is 41,024,000. So our reported distances are the same. And here are the 2 equal cost successors to get to that successor route. All right, so let's go ahead, let's clear the palette here, and let's go down a little further where we see the, where are we at? The loopback addresses that we have. So if we take a look, you can see that we've got these loopback addresses that were configured, the /30s, the 10.1.1.4, the 10.1.2.4, the 10.1.1.0/30, and we have their metric information here as well. All right, so let's take a look, or actually let's kill the debugs here on router 3, which is our router 8. We're going to say do you all to stop all debugging, and then let's say do show IP route EIGRP. And so right now, when we take a look at this, what is the only route that we're doing equal cost multipathing for? It's that 10.1.102.0/29. And again, all of these routes have selected a single best path, right? And it could be via the successor router 1, right, which is the 10.1.103.1, or it could be via the successor 10.1.203.2, which is going to be router 2. All right. We could certainly ping the loopback addresses, but again, I'm confident we're going to have reachability between all those loopback addresses. We've already looked at the show IP EIGRP neighbor output. So now what we're going to do on router 3, we're going to look at the topology table, which we sort of did already. Do show IP EIGRP topo. And so let's go ahead and take a look at the successor route here, this 10.1.102.0, and we can see we've got the computed distance and the feasible distance. If I were to copy that and come down and say do show IP EIGRP topology, and list out that specific successor route, you can see that we get all of the internal information. And this is a question that's going to pop up later on in this lab. It's going to ask, is there a way for you to see the metrics that are going to be calculated before they're actually shown to you? And the answer is yes, and this is the command. It's that do show IP EIGRP topology, and we get the total delay value, right? And we also get the minimum bandwidth value. So we're receiving those values, right? And that would allow us, if we wanted to go ahead and work the equation up. And so let's go ahead and take a look at what that would look like. So in this case, if we were looking at this here, remember the equation is basically only using by default bandwidth and delay. So it's going to be 256 times 10 to the 7 over the minimum bandwidth, and that guy is going to get added to the cumulative delay. So again, the total delay to get to that path, and it's going to be done in tens of microseconds, so we divide by 10. And then that's going to give us our answer. So if we take a look via this successor, here is and you can see it shows the feasible distance, which just happens to match the computed distance because the route just went from active into passive. So we would say it's going to be 256 times 10 to the 7 divided by the minimum bandwidth. Well, the minimum bandwidth shows 64 kilobits per second. And when we do this, we do the equation. Again, 64 kilobits is very, very slow. So when we do this equation, we're probably going to end up with a pretty large number after we do the division of 10 to the 7 divided by, and again, it's supposed to be done in kilobits per second, right? That's what this bandwidth value is it is kilobits per second. So let's go ahead and do the first part of this. Let me get the calculator up here. Let's put that there. And here's our calculator. Bring the calculator down here out of the way. And we'll say 10 to the 7, so 1, 2, 3, 4, 5, 6, 7, divided by 64. And that gives us 156,250. And so that is our K1 bandwidth value. Will be 156, and this is a pretty big value here, 250, right? And we're going to add in the cumulative delay. I don't need the calculator for the delay, right? Because we divide by 10, and all that means is I just scrap the last zero right off of the value. And so we end up with 4,000. 1, 2, 3. And that is our K3 composite metric. There's K1. And remember, the 256, who remembers why the 256 was added in there? Why are we multiplying everything by 256? Exactly. When IGRP existed, the predecessor to EIGRP, it was based on a 24-bit value, right? Well, the EIGRP composite metric for classic mode EIGRP or autonomous system mode EIGRP is 32 bits. And so in order to scale it to 32 bits, it simply needed to be multiplied by 256. Okay, so we've got our values here, so let's go ahead and let me switch over here. So now we're going to say this 156,250 plus 4,000 gives me 160,250, right? So pretty decent sized value, and we're going to multiply that by 256. And if all of my public schooling is going to pay off here, we should get 41 million, is that right? 41,024,000 and all zeros. So let's see, what do we end up with here? So let's clear that. Oh, actually, we'll leave this value here and we'll say times 256. And take a look at that. All right, all that time in math class was not for nothing. All right, so we end up with that value. So that's how we come up with the composite metric. Again, it's very straightforward. 10 to the 7 divided by the minimum bandwidth in kilobits per second plus the delay divided by 10 when we see, because again, it's shown in microseconds, but in the equation, we need to have it in tens of microseconds, just like when we go into the interface to manipulate that value. And again, it's very simple. Just drop the last zero off, and we're done. There's our tens of microseconds. So it's 4,000 tens of microseconds. We add these two numbers together, and then multiply by 256, and boom, there is our, at this moment, I should say the feasible distance when it went into the passive state, but that is our computed distance, right? All right, so that's how you configure, or that's how you calculate the EIGRP composite metric. So now let's move on to our next step, which is going to be B. It's actually asking us a question here. It says the most important thing is the two successor routes in the passive state on router 3. R1 and R2 both advertising their connected subnets because both routes have the same feasible distance and the same computed distance. Both are installed into the topology table. So the distance of 4 million or 41,024,024, which we just calculated, reflects the composite metric of more granular properties about the path of the destination network. And then here's the question. Can you view the metrics before the composite metric is computed? And I don't know if it's before it's computed, but it's before you see it in the topology table. And the answer is yes, it's that show IP EIGRP topology command that we just used. Now, let's take a look here on router 3. When I say do show IP EIGRP topology, we're going to see something interesting. So we've got equal cost multipathing from router 3 over to the successor route 10.1.102, and this is the transit network between router 2 and router 1. But you'll notice that we're not doing equal cost multipathing or equal cost load balancing to any of the other networks. But what if I were to say do show IP EIG topology all links? And now take a look at what you see for these loopback addresses here, 10.1.1.4/30. So when we say all links, if I see non-successors that show up here, what does that tell you? And again, can't focus on this enough. We've got our feasible distance here. We have our computed distance value there. And then we get this non-feasible successor who shows up in the all links output. And again, does he meet the feasibility condition? And this is a fantastic example of that statement, strictly less than. Because remember, the feasibility condition states that the reported distance of the candidate to possibly be a feasible successor, that the reported distance needs to be strictly less than the feasible distance, or in this case we're looking at the computed distance number, but it's the same as the feasible distance, of the feasible distance of the current successor. And again, strictly less than. Strictly less than. Because what are these two values right now? You've got it. They are equal. So this right here proves, because this successor, or I should say this non-successor, does not show up in the output when we do the show IP EIGRP topo. But it does show up in the all links output. And this is proving that in order to meet the feasibility condition, you need to be strictly less than, not less than or equal to. Because this would meet the condition less than or equal to if that was the case, but it is not. If it was less than or equal to, this successor would show up in the show IP EIGRP topology output as a feasible successor for this successor route, 10.1.1.4. But as we just saw when we rerun that command without the all links for the 10.1.1.4, is it there? It is not. So it is not a feasible successor. In fact, if I were to say, okay, I want to do unequal cost load balancing from router 8, who in the scenario we're looking at is router 3, to the 10.114, could I use the route through the 10.1.203? No, because the number one condition that needs to be met when we're talking about unequal cost multipathing using the variance command, the number one criteria is that any unequal cost path other than the successor has to be a feasible successor. And in this case, it is not, because it is not strictly less than the computed distance of the current successor. It doesn't meet that feasibility condition. Okay, so now what we're going to do is we're going to take a look at equal cost load balancing. And so from router 3, if I were to say do trace to the 10.1.102.1 and hit enter, you can see that the first packet goes to 103, and then the second packet goes to 203. So we'll hit it again, and you can see, then we get to our destination. So we go to 203.2, and then 103.2, and then 203.2. And then you can see it rotates around. And so we're seeing this asterisk here because the control plane policing is sensing sort of an ICMP attack, right? And so that's why we're going to get that asterisk back. And I'm having problems recalling the command right now. There's a command that we can run, and I can't remember it off the top of my head, that would stop the asterisk from happening, the asterisk from showing up. But it's not that big of a deal, because as you can see, right, when we run it, it goes 203, 103, 203, 103, 203, and the asterisk would be 103. And then 203, 103, 203, 103. So we are clearly load balancing across these two available paths. Now, it talks about Ceph, Cisco Express Forwarding, which is by default performing per destination load balancing. And so it's asking us to turn off, to say no IP route cache on the interfaces between router 3 and the other routers, and then it wants us to debug. So that's what we're going to do. We're going to get an interface serial 000. We're going to say no IP route cache. And this is basically disabling Ceph. And this is, don't ever do this in a production environment. You want Ceph to be running. No IP route cache. All right, so we've disabled Ceph. Now let's debug IP packet. And we're going to kick off a ping to 10.1.102.1, and we're going to say do ping 10.1.102.1. And I didn't even get that do debug IP packet. I was too busy typing. Now we kick off the ping, and there are the debugs that we're going to see. And so we're going to let's kill the debugging there. Now let's work our way back up to the beginning, and so you can see that's where we kicked off the debugs initially. So when we look at the debug output here, one of the things that we see, and where are we at? So we can see we've got the round trip average, and that's great, but the source IP is going to be the 103.3 interface. So it's the interface between router 1 and router 3, and that is the destination I'm trying to get to. That was the address I was pinging, and we're going to be going out the serial 000 interface. You can see down here we get this table ID, and we get the source and the destination again, and take a look at what happens. It says routed via the rib, right? And remember, in the rib, we had that equal cost multipathing. And so let's see, what else are we going to be taking a look at? And that's pretty much it, right? You can see that, again, the destination goes to the 102.1 and then the 103.1. So it goes to the link between router 2, which is, again, that's that interface, I'm sorry, that's the IP that we're pinging, but again, you can see that it's going to the 103.3 because it's routed via the rib. So EIGRP is going to load balance it anyway for us. And let's scroll down. We should see a Let me clear the screen here real quick. We should see a 203. See it going out the 203. No, those are multicast packets. Yeah, so it looks like the killing of Ceph, and sorry, I'm scrolling back and forth here. Yeah, the killing of Ceph makes sure that, in fact, it looks like we've broken the load balancing and that it's not continuing to load balance, at least not on this platform, because I'm looking for the 203 to see if it sends it to the 2033. And if I'm looking past that here, I apologize, but I only see the 1033 for those IP packets. And so by disabling the route cache, it's clearly only sending it that direction. Let's see what happens if we say do trace 10.1. What was the address we were doing? 102.1, 102.1. Yeah, so with ping, it looks like it's treating it differently than with the trace route command, that it is not doing the load balancing. Again, unless I'm not seeing it in here, but I don't see the destination going out. So there's our destination that we're going to, 1033, 1033. So yeah, I'm not seeing that 203. The link between router 2 and router 3 is not being used here, but the link between router 1 and router 3 is being used. Let me go all the way back to the top. I want to make sure I don't miss this here. All right. So yeah, so in effect, what we have done is we've basically, at least with the ping command in the debug that we were looking at, we don't see it going out to the 2033. All right. Now we're on to step 5, where we're going to analyze alternate EIGRP paths not in the topology table. And we've already seen that. So the question is asking us in step 5, why is there one entry shown in the topology table for the loopback addresses? And remember that it's not strictly less than, right? And we looked at that previously, so we're not seeing that when we look at the all links output. It is not coming back as strictly less than. And so then it says the reported distance of the loopback interfaces, or the question we're being asked is, what is the reported distance to R1's loopback networks using R1 and R2 as next hop routers when we're looking at router 3? And so it shows the reported distance. And again, on router 3, if I were to say do show IP EIGRP topology, and the network that we are curious about is at 10.120/30, which is right here. And it's asking about the reported distance. And so the reported distance is that 128.256. And then our computed distance, which at this moment happens to match the feasible distance, is 40,640,000. And so we could see that again specifically by saying do show IP EIGRP topo, and then just putting in the actual prefix itself. And then it's going to go ahead and show us those values. And again, we're interested in the link here, right there, between router 2 and router 3 in order to get to that network. All right. So when using the show IP EIGRP topology command, why is the route through R1 not listed in the topology table? And again, it's because it does not meet the feasibility condition, right? It is not the reported distance through router 1 is not strictly less than. So here it is through router 1, right? We can see from 10.1.1031, it is not strictly less than the computed distance of the current successor. And so then if the router 2 serial link were to shut down, would EIGRP route through router 1 to get there? Why isn't the switch to the new path as quick as it could be? And the answer is absolutely, right? So if we were to shut down on router 2, which is our router 9, and we want to make sure we get the right interface here, show IP interface brief, and we're talking about the link between router 2 and router 3, which is this one here, 10.1.203.2, so we'll say interface serial 010, and shut. It doesn't happen instantaneously because EIGRP, the diffusing update algorithm, now needs to step in and say, no, I now need to recalculate and perform the metric calculation to ensure that we have loop freedom, because there is no current successor, right? And so here's what I'm going to do. Let's do it and let's show you here. We'll say no shut. And we're going to bring that link back up so that on our router 3 here, which is my router 8, if I were to kick off a continuous ping and say ping 10.102.1.102.1, and let's repeat this a whole bunch of times. Right, so we're going to kick off this ping, and what we're going to do now is we're going to shut the link down to show that we have an impact here, right? And you can see that the interface has to go down. And we may have missed the dots. We'll say Control-Shift-6. I may not have to be able to go back all the way. But we should have seen a period in there somewhere in that output. And I'm not sure, did we? Yeah, unless it got lost in the output somewhere, we should have seen, because again, it's not a feasible successor. And so if I say do show IP EIGRP topology for the 10.1.102, see, we see this link here now because it's the only one that's up. But if I bring the interface back up and say no shut, and we allow EIGRP to go ahead and converge, the do show IP EIGRP topo for the 10.1, and actually it was the 10.1.102 here, it shows one successor. And actually they're having me ping, and this is the one that we actually ended up, I thought we ended up, yeah, that is the one that we do have a feasible successor for. So I apologize. I'm wondering if they've got me pinging the wrong address from router 3. So yeah, so it's almost instantaneous, because there is a feasible successor there. But if I were to ping the 10.1.2, let's ping the 10.1.2, and that's on router 1, I believe, if we were to say show IP interface brief. Is that what's over here? 10.1, no, it's all the 10.1.1s, so it must be on router 2. Do show IP interface brief. So there's that 10.1.2.1. So let's do this. There is no feasible successor for the 10.1.2.1. So we're going to say do ping 10.1.2.1, repeat a whole bunch of times. So router 3 is pinging that address. Now we're going to go to router 2. We're going to shut the interface down between router 2 and router 3 again. And we should see, and that was what we were looking for. But again, it's extremely quick, but we did drop, it looked as to be 2 to 3 packets, right? Because there was no feasible successor. So there's the first period. I'm not sure if another one gets lost, and then we've got that one there. So about 4 seconds, right? About 4 seconds of time that we had to wait for EIGRP to perform the diffusing update algorithm, right? To calculate the loop-free path. And you could even see here, we sent 5,151 packets, and so we did drop 3 packets. So we were missing. There was another period in there somewhere we missed. So, but 3 packets did drop, right? And so not bad, right? And then EIGRP quickly reconverges, and we are back up, and traffic is passing. So that's pretty good. So let's say no shut. We'll bring that interface back. So now it's talking about observing unequal cost load balancing. So here's what we're going to have to do. We're going to modify the bandwidth between router 1 and router 2 and router 1 and router 3. So the only 64 kilobit interface will be this interface right here, the 10.1.203, or I should say this link here between router 2 and router 3. We're going to change these to 128 between routers 6 and 9, and we want to make sure that we do it on both sides. It's very important that we make that change on both sides. So let's go ahead and jump into router 1, which is our router 6, where we're going to go into global config and say interface serial 000, bandwidth 128, and interface serial 010, bandwidth 128. And then we're going to do the same thing, but only in the one direction on router 2, which is our router 9. And this is going to be on the do show IP interface brief. So the link between 1 and 2 is going to be interface serial 000. Change the bandwidth to 128. And then we're going to do the same thing over on router 3. Do show IP interface brief. Should be serial 000 as well. It is. And so we're going to adjust the bandwidth value to 128. So now we're going to see some different things. So now when I say do show IP EIGRP topology, take a look now. By manipulating the bandwidth, we have actually sort of qualified some of these successors to become feasible successors. So remember, right here, the 10.1.2.4, there was no feasible successor prior to us making that manipulation of the bandwidth value. And now there is. So the 10.1.2.0 is the network it looks like we're going to be working with here. And does it meet the feasibility condition? Remember, the feasibility condition says that if the reported distance is strictly less than the computed distance, which happens to match the feasible distance at this moment. So we know that that went into active when we changed the bandwidth and now has gone into passive and is fully converged. So is 128,256 less than, and this is definitely not a rhetorical question because it's kind of obvious here, 21,152,000, and it is. So this is my feasible successor. And this is the successor next hop router, and this is the feasible successor next hop router. So this guy is already in the EIGRP topology table, so that if this successor next hop router went away, this feasible successor next hop router would step right in and take over. So let's take a look at the values that we're going to have here. IP EIGRP topology for the 10.1.2.0/30. And so there are the values. We meet the feasibility condition. So now I can use that path, or I should say, to that successor route, I can use the feasible successor to do unequal cost multipathing. And this is where we get into the variance command. So again, let's take a look at do show IP route for the 10.1.2.0/30. And as you can see, we only have the single path right now, the single successor, which is 10.1.1.0.3.1 for this successor route. Here's our administrative distance for internal EIGRP, and there is the current computed distance. So if we run that command here again, let's talk about what it is we have to do with the variance command now in order to determine what we set the variance to. So here is the current computed distance. Here is the current computed distance for the feasible successor. And so in order to come up with the value that we're going to use, we need to figure out, and again, there's two ways we can do it. We can divide the larger computed distance of the feasible successor by the computed distance of the, or we should be saying, I guess, feasible distance in this case. The feasible distance, which matches the computed distance, the feasible distance of the current successor, and we're going to end up with a decimal value of some kind that we would need to round up. Or, just simply by looking at these numbers here, I could say that it looks like roughly 40 million and 21 million, that if I were to multiply this by 2, it would be larger than the computed distance or the feasible distance of the feasible successor. So it would qualify it for unequal cost multipathing. So let's do this. Let's pull the calculator up here again. And if we were to do the math, and I were to say, okay, 40,640,000, 1, 2, 3, divided by 21,152,000, 1, 2, 3, and then say equals, yeah, we get 1.92. Now remember, EIGRP doesn't use decimal math. It uses integer math. So we're going to round up. Because if I were to say 21,152,000 times 2, is this going to be greater than or larger than the value of the feasible distance of the feasible successor? And yeah, 42,304,000, is that right? No, something went wrong there. 21,152,123 times 2 equals. There we go. So yeah, 42,304,000 is greater than the current feasible distance of the feasible successor. Therefore, it will qualify this feasible successor to participate in unequal cost load balancing. So what do we need to do? In order to make that happen, on router 3, we need to change the variance. So let's go into router EIGRP 100, where we're simply going to say variance 2. Because again, that variance value is going to now be larger than the feasible distance of the current feasible successor. So the two conditions that need to be met have been met. The first is, does the successor meet the feasibility condition? Clearly it does meet the feasibility condition because the reported distance is strictly less than the computed distance or the feasible distance of the current successor. So the feasibility condition has been met. Now the second condition we need to meet is to simply increase this by the multiplier so that it is large enough or artificially larger than the feasible distance, which in this case is also the computed distance of the feasible successor we wish to use. So now when I say do show IP route, for the 10120, take a look at what we see. And did it affect everything else as well? It did. Take a look. It affected a number of other successor routes. But we definitely impacted the one that we wanted to, and now we can do unequal cost load balancing across the two successors, router 2 and router 1, in order to reach the 10120. So again, we're just taking advantage of the additional path by sending traffic across it. So now the question becomes, what is the ratio? What would be the ratio between the two links? And so, because again, we're doing load balancing, unequal cost load balancing, so what would that be? And the way we would do that is we would divide the largest computed distance value, so we would say 4064,1234, and divide that by the lower value, the 2115,2123, and we see we get that 1.2 number. So it's 2 to 1, right? It's basically 2 to 1. So we're going to have 2 packets going across the original successor for every 1 packet, because it's about double there, right? About for every 1 packet that goes across this feasible successor, who's now being treated as if he was a successor route. But it's actually easier to see if we simply say, do show IP EIGRP topology for the 10.1.2.0 / I believe it's a 30. And is that the traffic share, or is it the... we want the route. Whoops, sorry, Control U. Let's pull this back here. Control U. Do show IP route for the 10.1.2.0. Yeah, it's the route. There we go. So we get the traffic share count. So the ratio is 25 or 48. For every 48 packets that come across this link, 25 packets are going to come across this this other link. And so again, it's almost 25 to 50. So you could say, you know, that it's almost 2 to 1, right? So 2 packets go across, or 2 flows would be sent, depending on the platform, would be sent over the one link as opposed to the other link. Okay, let's see here. And then we see the do show IP protocols, do show IP protocols at the very end to simply show us that the metric variance has been set, right? All right, well, I think that is it. This is going to wrap up. That's everything. So this is going to wrap up EIGRP Lab 2-1 from Cisco Networking Academy. Again, we talked about a lot of important things. We saw how we can calculate the composite metric and we can get that feasible distance value or the computed distance value. We saw how we can do equal cost multipathing. We saw how we could do unequal cost multipathing. And we examined the topology table. We saw that, again, in order to get that traffic share count, it's very easy. Just type show IP route for the specific prefix that you're trying to get it for. And again, we can kind of round this to a 2 to 1 equation, 2 to 1 ratio. If we wanted to be super strict and specific, we would say that for every 48 packets that go across this link, only 25 go across that link. All right, thank you so much for watching, and I will see you guys tomorrow night.